Okay, hey everyone. So, hey Thomas, yeah. So, actually, we're going to kind of combine the next two topics that were on the agenda, and kind of the reason for that is because they kind of go together with kind of the end goal of service chaining on overlay networks. Not that you have to tie NSH to LISP, but anyways, and a lot of the background work in implementing these protocols in Open vSwitch was kind of similar. So we thought it made sense to kind of combine, the two presentations here. So real quickly, we'll kind of quickly go over service chaining. I don't want to spend too much time on marketing type stuff, right? And then we'll talk about LISP and control plane service chaining. Kind of go into detail on network service headers, which is what NSH stands for. I think we talk a little bit about the problem in here. We'll talk about what work we've completed and what the next steps are and what we hope to accomplish after this. So this is, I think I promised, the only somewhat marketing focused or markety slide in the presentation, hopefully. So service chaining and network service headers. So I think most people are familiar with kind of service chaining, right? Service chaining, a broad term that describes delivering multiple services in a specific order, and this becomes even more interesting in the context of NFV, right? Like network function virtualization. So what does service chaining let you do? It lets you decouple the network topology and services. You can support dynamic insertion of services as things are running. There's kind of a common model for all types of services. This is what we're hoping NSH helps to achieve with this. So NSH is actually kind of composed of two things, as is typical with these things, right? There's a data plane implementation and the control and the policy side of service headers as well. So this example, in this example, like I said, we're going to kind of talk about LISP because LISP is an overlay protocol that we put into OVS maybe 6 months ago, but there's still more work ongoing with LISP there as well. So that's kind of a summary of that. So let's see. So I think Vina's going to talk a little bit about the background of LISP now too.
If it works, yeah. Okay, so I'll talk about, I'll just give a very short overview of LISP. And the focus is basically from the perspective of the control plane that enables service chaining, and then it goes well with the NSH descriptions afterwards. So LISP is a layer 3 overlay protocol. It has a control plane that was defined for it, and the control plane is decoupled from the data plane and provides network programmability. One of the main design goals of the control plane was to enable dynamic and on-demand tunneling. The data plane is just an encapsulation header very similar to VXLAN actually, except for its original design was for L3 in L3. It supports multi-tenancy. The control plane is very, in the most basic form, it's basically it stores a mapping of the overlay addresses or the virtual space to the underlying physical network. And within that mapping, you can also include some forwarding policy as well. The forwarding policy examples are traffic engineering, service chaining, which is what we talked briefly today, load balancing, and so on. So can we go to the next slide? Yeah. So this is a simple example of how, for instance, the traffic engineering or service chaining policy works in the control plane. So what happens is that a network virtualization edge or like a virtual switch would receive a packet for a destination a virtual destination that it doesn't have a mapping for or a flow for. So what it would do is send a request to this mapping system, which is the basic control plane of ours, and it will query the mapping, the physical mapping for that virtual address. And what it will get back is basically the policy for forwarding that to the right destination. And for the traffic engineering, we have this format called explicit locator path, where we give as well, basically the mapping system returns a sequence of encapsulation hops. And that basically defines the path, the traffic engineering path, or it can be service chaining as well. And then the NV basically will figure out where in this path it is based on the locator that it has, or based on the IP address that it has. And then it will program in the fast path the next hop for that flow. So on the fast path, basically only it will be a hop-to-hop forwarding. The next. Oh, actually, just one thing on the previous one. So we have a few flags there. There is a strict S flag for strict, which enables us to define hops that are not strictly to be enforced. So, for instance, if on the reachability of the data plane, the next hop for whatever reason is not reachable, or if the S bit is not set, you can actually skip that and forward to the next hop that you have reachability to. Another thing is the P bit is for reachability protocol that we run on the data plane. So that just indicates whether the next hop will accept those or is unable to respond to those reachability probes. And then there is an L bit, which is a lookup bit, which, for instance, if you have a service or an encap hop that has some sort of mobility capability, then you can basically build this indirection into it where when you get the re-encap hop, it's actually an indirection and you have to look that up again to find out where the actual location of that hop is. That's it. Sorry? Oh, so that's why, like, we're specifying, so usually in the basic version, you would request the virtual address from the mapping, look up the virtual address in the mapping system, and what you will get is the physical address that virtual address is mapped to. So you'll look up a MAC address and you'll get the IP address of the virtual switch. Exactly. So what I'm showing here is not the entire response that you get. I'm just showing here the version where you get a path instead of just a destination. So basically, there up there, if you look, we have the network virtualization edge, which is sending a request for a destination address, which we call it endpoint address or endpoint identifier, which is let's say a virtual machine's address. And you will look that up in the mapping system. And the mapping system returns to you either one locator, which will be the destination of the address of the, let's say, machine that VM is located on, or it will return to you a sequence of hops, which will basically define that path, the service chaining path, or just the traffic engineering path. And each locator here, which is the re-encap hop, will be basically, so you can have multiple hops. Here we have like 2 re-encapsulation hops. But you can have like as long as a path that you would want, and each re-encap hop basically has the same kind of Lisp stack. It would get the packet, decapsulate it, forward it to let's say a service or do some sort of processing on it, and then again re-encapsulate to the next hop. So that's how the path is defined. It's hop by hop. It's hop by hop, yeah.
This presumes that the management plane understands this policy. So I have 2 hops. When I get to that first hop, I just have to get to the second hop. Has to be predetermined.
So in the control plane, you would define the entire path. So basically, let's say in the mapping system, you have an entry for VM with this MAC address, or with this IP address, and then there you define the entire path of how to, let's say, reach to that VM. For instance, you would say for this particular prefixes, you have to go through a firewall and a NAT or whatever. And so then each let's say, agent on the virtualization edge would get the entire path when it has a packet matching that destination. And then in the data plane, only it will program the next hop for itself. Meaning that let's say, if we were to implement this, let's say in OVS, the OVS user space would get this. It will figure out where in the path or which re-encapsulation hop it is itself, and then it would program a flow with the next encap hop for that flow. Does that make sense? Yes. Mm-hmm. So there is some sort. This is probably not in the case of, let's say, data centers with enclosed environments and so on, but for cases where we have this Lisp has this reachability protocol where you can on the data plane figure out if the next hop is actually reachable because it's and so if the strict pick is not set, meaning that you have like a optional, let's say, service or an optional encapsulation, re-encapsulation hop there. It's better to pass through it, but if it wasn't reachable, we still want to use a different path to the next one. The default is the strict, yeah. Okay, next. So back to the data plane. As I said, it's we have the original version of Lisp was IP and IP. There are extensions for supporting Mac and IP as well, which would really look very similar to VXLAN, except for Lisp has a few more flags defined already. And so, actually, let's go to the next slide. So we've worked on this to implement it in OVS. The work completed already includes basic encap decap support and the flow-based tunneling, and we were very glad to see the flow-based tunneling in OVS because that kind of helped us with reaching the goal of doing dynamic on-demand tunneling, and not creating a port per destination. And so we have support for that in OVS, but not in upstream Linux. The Wireshark dissector for Lisp has been there available since 1.10. And the ongoing, actually the most problematic thing that we faced was that OVS was it is very L2 oriented. So obviously, and so even to define a flow, we had to have a Ethernet header. So to enable L3 and L3, which was the basic Lisp, we are working on enabling more generic layer 3 tunneling, and enabling having a flow without specifying a flow that does not have an Ethernet header. So basic push and pop Ethernet header was implemented. And so the work there is ongoing. Also, we needed to look up ARP tables to be able to, when we push an Ethernet header, to be able to push the right MAC addresses for the incoming packets based on their L3 header. And so we would. So for outgoing packets, we would pop the header, and then it will match based on the layer 3 address, the inner layer 3 address, and it will match a flow, and it will be encapsulated and go out. On the incoming, there is no Ethernet header, so we have to push one. That was the encapsulation header. That was the Lisp encapsulation header, which was very similar to. So do you want to go back? Yeah. So that's the encapsulation. We have the original packet with an IP header. Then there's a Lisp header, which is this enlarged piece, and then another UDP, and then layer 3 and L2. So there's no MAC address in the payload packet. We pop that, and it's L3 in L3. That's the generic Lisp. There is extensions to support Mac and IP, which would look very similar to VXLAN. And as you see, the Lisp header actually is very similar to VXLAN. The only difference is that a few more flags are defined. And actually, the flag number 4, which is instance ID in Lisp, is identical to VNI in VXLAN. Okay. So back to here, yeah. So that's what is going on right now. Lori Jacob is actually working on this layer 3 tunneling support, and hopefully we'll be able to submit the patch sometime in the next couple weeks. We're also looking into enabling Lisp control plane in OVS. Haven't started yet. We'll see how that goes. And another effort that is going on is the Lisp GPE. That stands for Generic Protocol Extension. So 2 drafts were submitted in IETF. I think that we're kind of trying to enable including, so a more generic format of including IP or MAC or NSH headers inside the layer 3 encapsulation. So basically, we would be able to put as the inner header of Lisp or VXLAN any generic protocol based on a protocol type. And so, yeah, I think Kyle's going to talk more about that. So with that, I'll hand it to you. Any questions on the Lisp slide? No. Okay. Thanks.
Okay. So let's see. I think we're doing good on time here. So, so I just wanted to. So this slide kind of touches on, the service chaining data plane components and kind of how they relate to NSH, which was what we're going to talk about now. So you can kind of see we've got four different components here: a traffic classifier, a service path, service overlay, and a context here. I think it's pretty straightforward. If you take a look at this as to what they do. So let me pop over to. So this is, and again, this NSH is also an IETF draft as well, and so this is kind of like what the basic header is composed of. It's got the base header and then these context headers as well. I think one of the key things that we had mentioned before was, the NSH header is really transport agnostic, so you can kind of stack it on whatever overlay protocol you want: VXLAN, Lisp, NVGRE, MPLS. I have some backup slides that kind of show that at the end, but it's pretty safe as well. And then the other key point here is that the context headers are going to carry the metadata along with the service path. And that all of that is likely populated by the control plane because it's the one that's programming these service paths as well. I have another slide that this one kind of goes into a little bit more detail on the NSH header as well as to what's in there. So as you can see, let's see, we effectively have 2 bits that are of significance at the front there, the O and the C bit as well. The O bit is the OEM bit. It's going to indicate if the packet should be punted or not. And the C bit indicates if context headers are there in it. And then we have the protocol type of the packet as well. The service index, so that's what's actually used, as it says, with the service path identifier to derive unique value, basically where we're going to send the packet as well. And then the service path identifier is the identity of whatever your service is, whether that's physical or virtual or whatever it is, but that's the identifier of where you're going to send it as well. And then the context headers are effectively metadata that the control plane can program that the services, will know about when it gets it there. So kind of tying this together a little bit at least, we put this slide up, and like I said, NSH is really protocol agnostic, but since we're talking about Lisp as well, we thought we'd throw up NSH plus Lisp. And as actually there's a mild problem with this this problem is actually addressed, as Vina indicated, by the IETF draft around generic protocol encapsulation as well here. So, but effectively, you know, Lisp has no mechanism to signal the presence of a non-IP payload yet, but GPE should help to solve that as well. So let's see. Getting to the interesting stuff here. So there's some more, you know, transport agnostic. Let's see, I think we talked about all of this. So, actually, hold on. I want to skip. I'm going to skip that slide just a sec here. Okay, yeah, let's get to the interesting stuff here. Oh, did we talked about Lisp, right? Okay, NSH work. So the NSH work that we've been doing, we started working on that this summer. So we started working on that in OVS, and we started implementing NSH initially on top of VXLAN in OVS, kind of as a proof of concept to try it out. And it turns out it was maybe not the best time to do it, as Jesse knows, with all the changes in OVS around upstreaming, you know, combining the tunneling code, right, collapsing it with the upstream tunneling code. We spent a lot of time rebasing and reworking that, and likely one of the things that we have to do is on the bottom there. You know, we want to move the NCAP, DCAP, the NSH stuff into the kernel rather than tying it into OVS, but it allowed us to kind of prototype this, at least initially, like that. So we did finish that. We tied that to the VXLAN code as well. One of the people working on it wrote a wireshark dissector as well. One of the interesting things that we did, as far as, you know, how do you program the NSH fields, right? How do you let a control plane do it? Well, the way that we did it was we decided that we were going to use the OpenFlow support in OVS for this as well. So we added support for that, for flow matching on the service path ID as well. And then we added support to OVS, VS Kettle, and OF Kettle for the above flow matching points as well. One of the, I talked to the, you know, Ben about this as well. How do we want to do this? And I mean, the real way to do this would be to work with like the ONF if we wanted to add new OpenFlow extensions to do this. So I think after talking to Ben, at least what him and I had talked about was we might add some extensions into OVS to allow programming this, because then what that allows is your controller to essentially utilize the OpenFlow control protocol to program the NSH stuff as well. So the next steps are the code. We were going to push the code last week, but in testing it, we hit, you know, after the latest rebase, we hit a bunch more problems. It may actually have been pushed this morning. I'm not sure, but we're hoping to get it out, if not this morning, soon as well, and then start iterating over it. Mostly we're looking for OVS people to review it and have a look and provide feedback. So, you know, one of the things, so let's see, the other thing we're looking at doing is add support for this NSH service index to be allowed to be set using this parameter as well, so we can set that as a flow parameter as well. And I think Vina touched on the Lisp stuff as well, as far as the next steps for upstreaming that. But Lisp is similar. So Lisp is, so Jesse, I think Lisp is the only protocol in OVS that's not upstream right now, right? Yeah. And so that's that's, and you know, and Lori's been working on that, but it's a bigger thing because of some of the L3 specific stuff. But so we're working on that, but the hope is to get Lisp upstream into the Linux kernel as well. So that's the work we have going on there. So I mean, if we look at what is kind of the end goal of all this stuff, well, you know, maybe the end goal is to allow kind of an elastic overlay based service network using NSH for services to be able to steer traffic to service VMs or even hardware that supports NSH. Utilize whatever overlay network you want for that. GPE, hopefully that will unify Lisp and VXLAN as well. You know, and then, well, how are you going to program all this, right? Well, then the logical thing is, why not utilize something like Open Daylight to actually program the NSH stuff as well. And then, and then you can tie Open Daylight into your elastic cloud platform of choice as well. So that's the thinking there. What made us use? I guess we could have gone either route, right? Because we could have done it using OVSDB as well. But I think the thought was that perhaps eventually we may want to try to, I mean, if NSH becomes useful and the community takes it up, it may be something we want to push into the ONF as well. So if we start out with this as an extension to OpenFlow that way, then it's easier that way. Oh. Well, I think it could be, and it seems like adding it as an extension initially is a nice way to see if it takes, if people like it, or what support it gets. Yeah. Yeah. And that's definitely a valid concern. I think it probably depends on your use case, I guess, on how much you're willing to tolerate on how much extra headers. That's a good question, actually. I mean, that's something I'd have to get back to you on, honestly. Yeah. You're in, okay. Yeah, yeah.
Platform, I would assume you could minimize, but
Yeah. I mean, it depends, right? I mean, you saw tons of context headers for NSH, right? So it kind of depends on what additional metadata you want and what the services need for that. So it's kind of variable. Not that variable-sized headers are very good, right? But so ILNP tries to solve a similar problem as Lisp, I believe, right? Yeah. So I think that's the best way to describe it. It's trying to solve a similar problem as what Lisp is. Was there an ILNP presentation? Oh, okay. Because I thought there was early on. I saw one. I know it would have been interesting, but okay. So let's see. I think I only have one more. Well, I think that's about it. Yeah, just a question slide. So, yeah. So any questions or no? Cool. Yeah. Well, okay, I'm going to answer quick, and then I'll let Vina either expand or tell me I'm wrong with what I'm saying. But originally, I mean, one of the big problems that Lisp was designed to solve was IP mobility, right? By separating kind of the endpoint, right, from how you get to the endpoint, right? So like, for example, an area where Lisp is used currently is for mobile phones with IP addresses as you're roaming across networks or between Wi-Fi and cellular and things like that. So again, it utilizes the whole mapping system, the control plane, and all that for that solution. So it was kind of designed to solve, I think, a slightly different problem, but maybe.
right. So it was designed initially to solve the overloading of the routing tables in the core. So it came from a whole different problem, and this dual semantics of IP address, where it both defines the endpoint and the location or routing address of that endpoint was a problem that was noticed that is leading to enlarged routing tables in the core. And so the idea was that there were different protocols, including ILMP, that were proposed to separate this identity of the endpoint from the location or the routing address. And that way, the connections or the layer 3, let's say TCP and layer 3 protocols the TCP sessions will connect to the endpoint address, which was decoupled from the routing address. And then there will be an encapsulation or something like ILMP, which is kind of playing with dividing the IPv6 address into two sections. And then you could actually aggregate, make the outer layer or the physical routing addresses more aggregated, versus the endpoints could move along and still don't clutter the routing tables in the core. So that was the initial problem, and that was and LISP was proposed for that. And because of the mapping system that it has, it could do dynamic kind of tunneling based on where you go. So it addresses mobility, but it was originally that's the purpose of original, but as you see, it fits very well in the network virtualization concepts because of that separation. So the ID will become the virtual address, and the location or routing address will become the physical address. And it also supports multi-tenancy, similar to VXLAN does, and so that's where we see it fit.
Okay. Thank you.